Okay, so I think today I'm going to cover only one last topic in logic, although there are a couple of other things. But for example, I'm going to cover what is known as rules of inference and why it is important. Because you saw that when we have bunch of propositions and there are a combination of it, right? And you want to evaluate it, right? Whether they are true or false finally, So we call them an argument where there are a bunch of basically propositions and one implies the other and so on and so forth, right? So there is a collection of these propositions is known as argument, right? And if you want to verify whether argument is valid or not, then there is a technique what we call as rules of inference, which is so there are certain rules which will simplify this observation whether the overall argument is valid or not, right? So I'm not going to give too many things. I'll just mention one or two rules, but everything is given in the notes. It's something very trivial thing, right? So, and then there is another topic which I'm not covering this time. Of course, this is a kind of it's obviously in your textbook as well. It's about normal forms. In the proposition logic, we have something what is known as uh, when you look at certain expressions, you can reduce them into a certain special kind of form. So there are two normal form, DNF, distinctive normal form and conjective normal form, right? So those are also a pretty straightforward thing. So I'm going to skip that. So I think we have done, about 2.5, so 2 lectures probably on logic till now. So this will be only rules of inference which we will be covering. If you want to know more about, if you are very much excited about logic, then you can look at the notes which we'll be providing anyway, or you can look at your book, or not last year but last to last year I have covered those things, so you can look at in the video lecture as well, right? So let us and then so basically after doing this rules of inference, I'm going to do certain basic things. I'll probably show you. So the building block of what is known as models of computation, which is very very important. And I think so for many of you, you will see that in your course curriculum, this models of computation or theory of computation, which is a part of discrete mathematics, is an elective course. But in many computer science, if you're doing BTech in computer science, this is a core course because we have a lot of other disciplines in our ICT. So this is coming as a elective for you. But I think so by doing that, many people actually miss this. So that's why we have included this portion. There will be about 5 to 6 lectures, which we will be covering certain basic things about the fundamentals of computer science. Very, very important topic. Okay. So this will lead to even compiler construction and other things. And, it's a very, very basic fundamental thing. And you will enjoy it. So like Mool Tattva of computer science, right, is there are only 4 kind of machines that you can build. One is finite automata, and very nice example is vending machine. You put some coin and maybe chips packet is output. So okay, this is a nice application of finite automata. Okay, there are plenty of other. For example, when you enter into an elevator and you press I want to go to floor 5, so that logic is also built on finite automata. So there is one input and then some action is taken and you arrive at some other output, right? Okay, so that is one very basic machine. And there are different kind of variations of finite automata with different kind of applications, for example, speech processing and so on and so forth, variety of applications. So I'm not going to talk about those applications yet, but at least I'll give you certain basic things about these finite automata. Okay. The next machine is push down automata. So finite automata, there is no memory actually. Okay. So there is no memory. There is input, there are states, and you move from one state to the other state, right? Based on that input. And when you add a memory actually, then it becomes push down automata. Same finite automata with their stack memory. You can push or you can pop something out of that stack memory. Okay, that becomes push down automata, PDA. Okay, so a little bit more powerful than the finite automata. And then from uh, push down automata, there is another version which is actually a computer, is Turing machine. Turing machine is a very very beautiful fundamental thing. and I think some of you must be knowing about it if you are interested in computer science. And as you know, that Turing machine was invented by Alan Turing while trying to solve a fundamental problem that was posed by David Hilbert in 1900. So David Hilbert posed around 23 problems. One of them resulted in actually designing this Turing machine. It's a pen and paper machine, which is as powerful as your laptop or your computer that you see use today. Okay, so it's very fundamental. So it's kind of benchmark, right? If you look at any computational process anywhere in the nature, and if you want to know whether you can do computation similar to your computers, so you just want to match it to a Turing machine. If you can do it with a Turing machine, certainly you can build things. How you will realize it physically, it's a different concept altogether. But so for example, these computers use semiconductors, right? Or the circuits based on semiconductors. So somebody has shown that there is a circuit equivalent representation of Turing machine. So basically, whatever you can do with a Turing machine can be done by the bunch of circuits, and so we can have a circuit representation of the computers. Okay, so that is a very basic thing. So, and there is a special kind of Turing machine where the tape has a limited memory that is known as linear bounded automata. So, top is a Turing machine, linear bounded automata, a little bit below than that, push down automata, and then finite automata. These are the core machines. So, essentially, मूल तत्व, right? शास्त्र अनंत है, विद्या का पारावार नहीं है, ऐसे में मनुष्य सदैव मूल तत्व पर विचार करना चाहिए. And मूल तत्व is there are only 4 kind of machines in computer science. Okay, what are these 4 machines? Finite automata, push down automata, linear bounded automata, and Turing machine. And in all these 4 machines, each of these machines accept certain languages, right? So I'll tell you about those. And each of these, so each language has a grammar, right? Whenever we are talking about language, so in the sense of computer science, language means bunch of strings over some alphabet. Okay, so for example, bunch of binary strings is also a language. Okay, so each of these machines accept certain languages. Each language has a grammar. So basically there are 4 kind of grammars, and this grammatical this classification in terms of grammar was given by a linguistic person, Noam Chomsky, right? So he is a linguistic person. When you observe things in nature and in the languages, he actually gave these 4 kind of grammars are possible to generate the languages, and actually they are matching with these 4 kind of machines, right? So it's a very, very fundamental thing that you should know about computer science, right? Now, so we'll talk about some of the relationship of these machines and couple of examples. I'm only going to do examples, no theorems at all, right? In all these 5-6 lectures, you should appreciate the beauty of these machines, right? And so in order to do those things, I need to cover certain basic math, which I'm going to cover towards the end of the lecture. Okay, and I think if time permits, I may also look at another very important aspect. I'll only give you one example of what is known as codec. So codec is basically encoding and decoding machine or device, or you can say algorithm basically. So whenever you are sending data from one place to the other place, means transmission, or sending a data from now to then, that means storage on any computer or device, you require codec or error control coding. Okay, because whenever you are doing these things, von Neumann has said that whenever you are going to process information, whether it is bits or whether it is qubits, if you are looking at quantum computer, errors are bound to happen. And in order to prevent, you need to have some sort of error correction mechanism or algorithms. Okay, so although the oldest code, I would say, in terms of the definition of codes, are nothing but bunch of binary strings, is as old as Pingla has invented some of these things earlier in India. But actually using these ideas into error correction was done by Richard W. Hamming in 1947. Actually, he invented it in 1947, and the paper was published in 1950. Okay, so because of the patent issues and so on, right? And that became the fundamental backbone of entire computer industry. If you are going to design a chip or VLSI thing, you require error control. Doing anything, it's a very beautiful branch known as coding theory or error correcting codes. Okay, I'll give you just one small example of that. Of course, there's a whole course. on my channel, it is available. If you want to learn those techniques, it is available, right? And the basic math that you require is a bit of linear algebra. I think you have not done linear algebra course, right? So yeah, so that course is required, and linear algebra is very important. You should do as early as possible because your machine learning or everything is based on linear algebra only, right? So that is very, very fundamental course anyway. Okay, so I think that's all about. So let me start with rules of inference. I'll give you a few things and then we'll move on. Okay, so in order to describe these rules of inference, I'm going to describe what is known as arguments. So basically, argument is nothing but a sequence of propositions in proposition logic. By the way, I think I should mention you something about here whenever we are talking about argument, that you must have used this word argument, right? People are discussing, making arguments, right? Argument, counter argument, right? So I have a theorem. Maybe let me see if you can prove it. And I can actually, I have not proven it, but I'm giving you an example. No matter how many people are discussing, so they are doing all these discussions, argument, counter argument. Whenever these things are happening, you can actually reduce all these arguments to certain fundamental arguments, and there you know how to win. So you can win any conversation if you can convert. So what are these fundamental arguments in your daily life? You can observe that, there are certain very, very fundamental things for which you don't have any counter argument. I'll give you just one example, and that will make my point clear. One very simple example is, if I say that in our daily language, whatever is happening is predefined. So this is a statement, Now, can you provide a counter example to, counter argument to this? You say, no, I have a free will. If I want to move my hand, right, I can do that. I say that is also predefined. You wanted to move this, and so can you provide a counter argument to this? I'm just giving you some very, very basic examples. So so basically, whenever you're having any fight going on between people, if I know many of those basic arguments, so fundamental arguments. So whenever conversation is going on, you can reduce everything to the certain fundamental arguments, and there this guy has no counter argument, so you are going to win the discussion. Okay, just an example I gave you. Now let me come back. So a sequence of proposition is known as argument here. Okay. So all these propositions in the sequence are known as premises, and the final one is known as conclusion. Okay. And we say that argument is valid if truth of all its premises implies is that conclusion is valid, that conclusion is true, right? So there are a bunch of propositions, right, sequential propositions, and I'm saying that final proposition is known as conclusion, right? And all other propositions in the sequence are known as premises, right? So if we say that an argument is valid, right, if truth of all its premises will imply that the conclusion is true, okay, then we say that the argument is valid argument. Okay, so argument is nothing but sequence of propositions. Proposition 1 implies proposition 2 and so on, whatever, so all the previous ones are known as premises. If all of them are true, will imply the conclusion is true. Okay, and then we say that argument is valid. So let me give you one example here. is a statement. You have a current password. And Q is a statement. You can log onto the network. Okay, you have a current password. Q is you can log on to the network. So I want to know whether P implies Q and P, therefore Q. Is it a valid argument? So if P implies Q is true and P is true, then Q will be true anyway, right? So we call it as, therefore, assuming P and Q are these two things I am saying, right? So P, you have a current password. Q, you can log into the network. P implies Q should be true and P is true. Therefore, Q is true, right? So this is a valid argument. The question is, this is a valid argument? Answer is yes, this is a valid argument. And actually, you can clearly see that this means that P implies Q, meet P, Q is a tautology. Right. So this is nothing but a tautology. So this is a kind of simple argument here, observation. So I'm going to give some rule of inference and their name. I will just mention one or two basically, and you can look at the table later on. Tautology and the name. Okay. P implies Q, therefore Q. P meet P implies Q, and the name is modus honest. That is the name for one of them. Similarly, I can mention negation of Q. So P is true, P implies Q is true, therefore Q is true, right? So that means there is a tautology. Negation of Q is true, P is going to Q is true, therefore negation of P is true, right? So similarly, we can have P implies Q is true, Q implies R is true, therefore P implies R is true, right? So you can actually make these kind of statements. I think I do not have a table right now to show you, but you can look it in the notes, okay? Okay, so I think using these rule of inference, you can actually find out many simplifications in the arguments. I'm not going to look at any of those things right now. Anyway, you can complete the table. So what you need, a cup of tea and then completing the table, right? So, I mean, it's something, right. So there are a couple of things. I mean, I can keep on writing, but it's okay. Okay, so now let me show you. Suppose I have two messages, yes or no, and I want to send it over this channel. So yes means 1, no means 0. So if I send 1, so 1 bit I am sending, what you are going to get? Either you can get 1, or if it flips, you can get 0 also, right? So normally, so error may happen. So if you are assuming simple error model, bit flip model, okay, in the bit flip, 0 may flip to 1, 1 may flip to 0. You can think of it like, when you're reading a signal as a threshold of some voltage, right? And if it is above that threshold, you assume it is 1. If it's below that threshold, then it is 0, right? So voltage fluctuation may happen, and then you are sending 0, actually you are getting 1. That may happen, right? With certain probability of error, P, say. Okay, so those things are pretty common. So the question is, how do we protect this data? This 1 and 0, how do we protect? Any idea? Very simple logic. If I say something to you and you are not able to understand, so what you do? Huh? Ask again. You will say, can you repeat? So repetition is a crude form of error correction, right? Whenever you are not able to understand, you say, please repeat. So here I am going to use that crude form of error correction. So rather than sending 0 or 1, let us see what I can do. So rather than sending 0, I will send 0, 0, 0. And rather than sending 1, I am going to send 1, 1, 1. So 0 means no, this, okay. You may say that why you are repeating 3 times. So I will discuss, if you do it 2 times, what will happen. So I'm assuming, suppose we are repeating 3 times. And now I am sending, in place of 0, I am sending 0, 0, 0. Right? It's a very basic philosophy, right? गुच्छे में रहोगे तो ताकत है, right? So if there are so many things together, you can correct. Let us see how. I am sending 0. Suppose I have sent 0, 0, 0. And I receive, middle bit is corrupted. Now what? How do we correct? So I know I will take 0, 1, 0. So suppose this is our vector x, this is vector y. I take y, which is 0, 1, 0, and I compare it with, because I know either 0, 0, 0 was sent or 1, 1, 1 was sent, right? I want to check which one was sent, right? So what I'm going to do, 0, 1, 0, if I ask this question, 0, 1, 0 is close to this or close to this? Now, closeness means number of bits they differ. Okay. If I assume this simple closeness formula, 0, 1, 0 is close here. So number of bits they differ are 1. And here 2. Most likely this was sent in that case. Right? See? Very, very crude analysis saying that, whatever I received, okay, I compare, because I know that what was, from where the data is sent, either this or this. Right? So either I just compare whether this was sent or this was sent, right? So just compute. So basically, whatever I am telling you, I can call it as a distance. It's known as Hamming distance between two vectors x comma y is number of places they differ. Very simple. Now you know that distance in calculus, you have done calculus, right? Distance, on the real line, distance between 2 points is x comma y is mod of x minus y, right? In r square, the distance is the distance between x comma y can be defined in terms of square root and so on and so forth. You remember, right? You can also define distance in terms of maximum of difference and mod and all those kind of things. Or you can also talk in terms of Manhattan distance. All these. So distance has certain properties. Number 1, distance is non-negative and 0 if and only if x equal to y. Number 2, it is symmetric. X comma y, same thing as y comma x. Number 3, it satisfies this triangle inequality. Distance between x comma y is at least x comma z plus z comma y. So z you are inserting in between, right? So now there is a t time problem. You show that this distance is actually a distance. Okay, so this is actually a distance. How will you show? Distance is defined, number of places. So x is equal to x1, x2, xn. Y is equal to y1, y2, yn. There are two vectors. Distance between x comma y is number of places they differ. And I am assuming everything is bits, 0 or 1. Right? Show me that this is a distance. So you need to first show that this is always a non-negative number. Obviously, that will be true because you are counting how many places. And is 0 if and only if both the vectors are same. So first condition is pretty easy to verify. Right? If x and y are same vectors, then the distance will be 0. What about the second property? Distance between x comma y is same thing as distance between y comma x. Symmetry. This is also true. Number of places x and y differ is same thing as y and x, right? So only one part is left, which is triangle inequality, and for that you require tea or coffee, right? Show that third property. So just try. It's a beautiful thing. Show that triangle inequality holds. You know triangle inequality? I am assuming you are all JEE aspirant, right? So you know. Huh? Not JEE. Physics wala, huh? Yeah.
वो क्लोज टू 0 0 0 है. So ये भी तो हो सकता है कि वो जो बाकी मतलब आपने assume ही किया है ना कि
No, I am saying that I'm assuming नहीं किया है. I'm just saying that I wanted to. So see, x was sent, 0 0 0 was sent, and some error has happened. Right now I'm assuming 1 bit flip is there. I'll show you 2 bit flip also. Okay, 1 bit flip is there. So I'm saying suppose middle bit is flipped. Now I have to find out which one was sent. So what I'm doing, I'm just comparing with the actual vectors which were available to us, right? So distance between y and the first 0 0 0 is 1, and distance between y and 1 1 1 is 2. Huh? So that means most likely, because whatever is distance is less, that is what. I'll show you the 2 bit also. So T problem, I hope you remember that if you basically you have to show that triangle inequality holds, and there you have to really think a little bit cleverly. So good problem. Okay. Okay, now suppose 0 0 0 is sent and 0 1 1 is received. Now what? 2 bits are flipped. I mean, so what I have shown right now, I've shown middle bit is flipped. If this bit is flipped, then also no problem. You can do the problem solve you can in the same way, or this bit is flipped, then also you can solve the problem in the same way. But suppose 2 bits are flipped. I'm assuming that suppose now you received 0 1 1. Now, can you work out this scheme? It will not work. So essentially, our repetition of 1 bit into 3 bit, this is codec is not going to work. I need to modify the codec. So can you think using your brain how many? Yeah, it's very good. 5 times if you repeat, you will be able to correct 2 bits of error. Not 4, 5 times. So see, now I think if you think a little bit, actually here if you repeat only 2 times, you will see that you are not able to correct. In that sense, that you're just computing the distance and see which one is closer. Okay, right? Got it? So basically, how many times you need to repeat? Odd number of times. Very good. If you want to correct certain bits. So basically, if I use 0 as 0 0 0 n times and 1 as 0 0 0 1 1 1 n times, if I repeat, and then n should be odd, then we can correct how many errors? Again, a t time problem. There is a formula actually, you can tell how many times you can correct. So actually, I should tell you briefly the distance, whatever we computed. So this whole thing is nothing but a space or subspace. You know about R cube. R cube is a space, three-dimensional vector space, right? X-axis, Y-axis, Z-axis, right? So any point can be written as a linear combination of three unit vectors, E1, E2, E3, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, if you remember, right? So that's the basis. So I'm saying that this is actually a subspace, and this subspace is used to correct single bit. So there's a whole idea about this thing. Actually, here you are wasting a lot of resources. People have asked this question. Okay, if I have to correct single bit, I am repeating 3 times. If I have to correct 2 bits, I am repeating 5 times. If I have to correct 3 bits, I am repeating 7 times, and so on. We can keep on doing this. So the question is, are we repeating, or can we do even better than this scheme? So answer is yes, we can do even better. And that whole branch is known as error correcting codes or coding theory. So you can look at some lectures. So it's a very beautiful application of discrete mathematics. So I thought I will just give you some idea about error correction. Okay, how this happens. Whenever you're listening beautiful MP3, it involves codec. If you are watching any movie, it involves codec. Okay, CD, DVD, hard disk, pen drive. Without codecs, they are not going to work. Right? So it's a very, very fundamental thing. So what are the error correcting codes behind? So one popular error correcting code is Reed-Solomon code, which is very, very popular, used in CDs, DVDs. You might have you used CDs before? Yeah. So CD, DVD, high density, high definition DVD, they all use improved form of codec, error correcting codes to correct errors. Okay. And so there are two kinds of codecs. I mean, error correcting schemes. One is, so basically this is known as channel. You are sending something, you are correcting. There is another one is source coding, means data compression. So later on in the course, we are going to look at Huffman codes at some point of time, right? Huffman code we will see. For example, you look at English, right? So English, which letter appears quite often? E. So probability of occurrence of E is very, very. There's a famous paper by Hux and Piper which talks about the statistical analysis of English, right? So basically, since E occurs more, you can use less bits to represent E. For each alphabet, you can use certain number of bits. So which one is having more probability of occurrence, you use less number of bits. With these kind of things, an efficient coding scheme has been discovered, known as Huffman coding for data compression. Okay, so all your data compression algorithm, I think you must have used gunzip or zzip. Linux people might be remembering, right? Zzip algorithm. Limpel-Jeb has formulated that algorithm, which is used in zzip. All these are beautiful mathematical stuff. So if you are curious, or you want to learn, or you want to come up with your own algorithms, you need to look at these codecs, right? And see the beauty. If you can come up with a new scheme, that will be you can start a company also, right? See, for example, you have heard Qualcomm. The Qualcomm founder was Andrew Witterby. Witterby was teaching this course of codecs to bunch of students, and then while teaching a decoding. So whenever you're doing encoding like this, you should also have a decoding algorithm which will decode the. So while decoding, there was bunch of codes known as convolutional codes. So he was looking at these. Encoding was very easy. It uses some sort of finite automata. While trying to decode it, he realized that the decoding that was given in the book was very tedious. Sometimes I also don't like when you read some book. If something is too complicated, it's of no use, right? So he sat down one evening and worked out his own decoding algorithm, and that became the fundamental Viterbi decoding algorithm used in so many standards everywhere, and he formed the Qualcomm. So one algorithm one company, right? Solid algorithm, solid company. So for that you require bunch of tea and coffee and thing, right? Okay, so fine. So this is all about error correction business. Now we can move. So here I am going to use, in the next 5-6 lectures, I am going to use the slides of Professor Bush from LSU. I think now he moved to some other university, but he has given me permission to use his slides. These are very beautiful slides. I mean, if I have to make it, it will take a lot of efforts. But I think in some of this one is easy, but the rest of things are pretty, good things. So let me show you. Sets, सेट तो आते ही होगा ना, जेई का एग्जाम दिया है तो. So give me an answer. Set is a collection of well-defined objects, right? ये तो याद होगा. Set is a collection of well-defined objects. Give an example of a collection which is not well-defined. So give me an example of a collection which is not well-defined. What does that mean? Yes.
My favorite book or my favorite cricketers. It is not well defined.
Why? Because you must be having some. So what do you mean by, first of all, what do you mean by well-defined? No. Well-defined means, no. Well-defined means you should understand. Then you answer this question. Well-defined means given a collection and given an object, you can certainly tell whether it belongs to this collection or not. Okay. So that is the meaning of well-defined. So you need to give me a collection for which you cannot tell if an object is given whether it belongs to that collection or not. So what you require? A cup of tea to think. Okay. So your set theory, I am taking exam of your set theory. So okay, now we should check some more concepts. Okay. Collection of objects, this and that. Set representations, this you know already. Universal set and so on, right? Set operation, union, intersection, difference. If you don't know anything, just raise your hand and we can discuss. Complement of a set, that also you know. De Morgan's law, no problem. Empty set is pretty beautiful set because that is having no element. And so union, intersection, and so on and so forth. These rules are straightforward. Yeah, subset is a beautiful thing, right? So let me ask you one question. We know that A is a subset of B if every element of A is a member of B, right? So now proper subset means if it's a strict subset, right? Equality will never happen, right? So that means cardinality of A is less than cardinality of B, right? Number of elements in A is less than number of elements in B. Now, if you look at this set of integers, how many elements are there? Infinite. And set of even integers, how many elements are there? Infinite. But even set is proper subset of integers. How? Beautiful question, right? Who can answer?
For every integer, even number will jump twice in comparison to a single integer.
So this is something fundamental. I think at these things probably when you first time you studied set theory, class 6, 7, 11th. Acha. You study in what, 6th? 8th. You see, people are studying set theory in 8th. So now, but this question you encountered. Now I am going to ask you one. So there is one very popular hotel, Hilbert Hotel, you know. Have you heard Hilbert Hotel? They are infinite rooms, right? And suddenly there was a wedding bus came actually, and then they have say 56 people, and the hotel was completely packed, no room was empty. And then the manager said that, okay, I can arrange all the 56 people. So he asked everyone to move 56 times to the next room, right? Keep on. So that all 56 people can still go inside. So this is the beauty of infinity, right? So this is Hilbert Hotel. And that's the reason this business is not going to work here, because 2z is infinity, that is infinity, right? It's a subset, but both are having infinite cardinality. See the beauty, right? If you don't understand, you can take a cup of tea and think, right? Okay. So that's all about. By the way, how will you show that both set of integers and set of even integers have same number of elements? I think this also you might have read in calculus class, right? Countable and countable. It's very, very important, by the way. So you can count. Basically, there is a 1-to-1 and on-to function from z to 2z. F of n is equal to 2n. So that means if you give me one integer, I will give you one even integer. For every integer, I will give you one even integer. 1-to-1 correspondence. So that means number of elements are same in both the set, right? Got it? थोड़ा मुश्किल से believe हो रहा है? Counterintuitive? Actually, in infinity, the theory of infinities are very beautiful. One can ask different kind of questions. Number of elements on the real line, number of elements on the set of integers. What is the relationship? Or if you take an interval on the real line, number of elements in that interval, what is the relation? So when Cantor gave different kind of infinities, people said this guy is mad actually, what he's talking about when he wrote the first paper. If you really want to enjoy that beauty, you can search on the internet, the paper by Cantor, George Cantor, beautiful paper, okay, about infinities. Disjoint set is okay, cardinality, number of elements. Power set is very, very important concept, by the way. You know that this is used a lot in your algorithms. So if S is having 3 elements A, B, C, power set is this, right? Empty, A is there, B is there, C is there, all 2 pairs and then 3 pairs, right? So you can represent this as 3 bits, 0, 0, 0. Neither A nor B nor C. Only A, no B, no C. No A, only B, no C, and so on. So each power set can be represented by bits. Beautiful concept actually. It is used in doing certain calculations. Later on, you will observe this, okay? It's a very, very important representation. Cartesian product is fine. This you know already, right? Functions. Falan, right? Falan. In Hindi, they call it falan, right? So functions, if for every domain, if for every element in a domain, there is a rule which associates to every element in a set A, giving unique image in set B, then that is known as function. So can you give an example of a rule which is not a function? ठीक है? तुम तो अभी कैलकुलस पढ़ के आए हो? नहीं ना? Beauty. Calculus is full of beauty. By the way, I ask you one question. Who invented calculus? Who invented calculus? कुछ नहीं हवा है, पता नहीं क्या पढ़ के आए हो, right? Calculus की पहली टेक्स्ट बुक कब लिखी गई थी? The first textbook of calculus, 1535. Yukti Bhasha. You can read that book. Actually, it is available on, published by Springer, now. Yukti Bhasha, okay? So you can look at this, Madhvacharya from Kerala School of Mathematics and Astronomy. So they have, and this is, Newton came something around 1640. So there's a huge gap. Okay. Because of love of, or because of beauty of mathematics in our daily life, in India, we had a lot more interesting things. For example, trigonometry, invention of trigonometry, this planets and Jyotish and all kind of things. Varamir, I think you might have heard about some of those things. Ujjain was very famous for many activities. Anyway, so these are something interesting thing which you can look at it. So relations. So here actually many interesting questions can be asked. What is the relation? Any subset of A cross B is a relation, right? If A and B are two sets, you know this definition. So I asked different questions. How many? So I think you know that relations are of three kinds: reflexive, symmetric, and transitive. So suppose A is a set having n elements, B is a set having m elements. How many equivalence relations are there? Beautiful questions can be asked, right? Or how many symmetric relations will be there? These kind of questions are very common in your interview, in your job interview also, right? So one can ask these questions. Reflexive, symmetric, transitive, right? Equivalent classes. You already saw this business, equivalent classes, right? Can anyone tell me which one? The first day we talked about modular arithmetic, integer modulo n. So what we are doing, take all integers. Say for example, I am looking at integer modulo 2. So n is equal to 2. So I'm dividing all integers by 2 and looking at the possible reminders. Either reminders are 0 or reminders are 1. So these are two equivalent classes which will partition the whole set, right? So normally equivalent classes partition the whole set, It's a very interesting thing, beautiful thing. Graph तो बहुत आसान है, we can leave that, By the way, you know what is this? Huh? No. It's a Hemchandra number. Hemchandra sequence, It was discovered by Hemchandra and other people in India, Patan, near Patan in Gujarat only, Some Jain Muni, some mathematicians. So later on, Fibonacci used them, and so now, because Fibonacci introduced these numbers in Europe, so it is called on their name, but actually they were discovered in India. They were discovered in music actually, while forming music and many interesting things. Okay. So, by the way, I think uh, since we are here, I should tell you that you go to this website, Google, and type NJAS. Sorry. OEIS. Online Encyclopedia of Integer Sequences. So actually, every lecture, every class we introduce this. So this is an opportunity, just like that. Now these numbers are known as Fibonacci numbers. You can get numbers on your name if you discover new numbers by registering here. By the way, every class, whenever I taught this, there are students who have got numbers with their name. So if you search here DICT, you will find many of them actually. So see, I think this was discovered by probably Rachit Agrawal, I guess. No, which one? Who is the author? At the bottom, you can see the author. Yeah, Rachit Agrawal, right? So many things are there. Who is the author? Yeah, you see here is a Rachit Agrawal, right? He was one of your student at DICT. See, DICT email address is also there, right? So he discovered this sequence, numbers multiplied by 4 and written backwards. It's new sequence, right? So like that, every class, there are students who registered some numbers on their name. So it's a good way to get some publicity and you can have your name. So you try discovering some new sequences and then register them. Okay. So this was started by Neil Stone. Is okay. He collected all these sequences and why these are important. Suppose you are doing some work in chemistry. I'm just giving an example, and you encounter in some counting some integer sequence, and someone else is doing some problem in electronics or VLSI design, and he encountered some sequence. So now that problem, if you know how to solve, you can find a solution to a problem here because the integer sequence is same. Okay, so this is where things are connected. Okay, so there is an article also Google of Mathematics which talks about many things. So I hope you will use this. You know, I have also discovered one sequence. I mean, of course, I can write more, but I have not done. But there are people who have used our work to discover to get some new sequences, you know, on their name. Okay, so if you search my name, you will get one or at least one sequence you will get, right? So this is, I think, all Rachit Agrawal. So Rachit Agrawal, within 2 days, he discovered 9 sequences and registered. And because of this, Neil Stone, who was AT&T fellow, so he wrote him a special email and thanks, kind of thing that he did this, you know. So I think some of you can also do that. I think Rachit is right now at Intel, if I am right. So I think there is another person who discovered data wala. Maybe I forgot the name of the spelling, but of course you can search actually, you know. So this is pretty interesting. So if you want to, for example, if I look at 1, 1, 2, sorry, 1, 1, 2, 3, 1, 1, 2, 3, next 5, then 8, 13, and you enter, you can find the formula also, right? So basically this is, so you just enter few initial sequences and you can find the formula. By the way, do you know why this series is quite famous? Have you gone to US? Or you will be going in the future? So you see, this can be used, this series can be used for converting kilometer and miles. So you see, if you say that 3 miles is equal to approximately 5 kilometers. 5 miles is equal to approximately 8 kilometers. 8 miles is equal to approximately 13 kilometers. And this gets better and better as you move along. Okay. It's a beautiful conversion formula, right? Okay. Okay, so this is something interesting about numbers. So I think if you want to have love with discrete maths, you should play with these numbers and see how many of you will try to get a sequence on your name. No one? Good. Only 1, 2. सबको कोई मतलब ही नहीं है कि कॉम्पिटिटिव प्रोग्रामिंग 3 कॉम्पिटिटिव प्रोग्रामिंग करेंगे जॉब मिलेगी बाबू बनेंगे बाबू बनने से कुछ नहीं होगा right? I think Bill Gates has given a statement why there will be no Google or Microsoft like company in India because people are trained to become babu and not a leader. This is a statement you can read. Okay, so Okay, fine. So I think I'll stop, and then maybe in the next class we'll do few more things. Thanks.